I got emails from a number of students asking for an extension on this homework. And that's fine. I hadn't anticipated that the jump to working in multiple dimensions was going to be as difficult as it apparently was. But since I granted that extension to some students, I'm happy to grant it to other students as well. That being said, I still hope that some of you are willing and able to present what you did today, and that we can talk through some of the issues that caused you to have difficulty with doing this assignment in multiple dimensions. I know there's a few tricks that we maybe didn't cover as much as we should have prior to the assignment, and so I want to go over those, the points at which you guys may have been stuck, and talk about how to resolve some of those. So what we have today is, last time we went over auxiliary filters, and today we've got primarily homework 4 presentations, and then I was able to get one case study about frequency tracking, and I've got a number of things to talk about with that. This is some work that I've done previously, and it's a really nice application of tracking a tracking problem that doesn't involve tracking a physical object that's moving. So many of the tracking problems are about tracking people or ships or boats or bad guys or what have you, and this is an example where you're tracking something else, and it works really, really well. So we'll spend some time going over that. Before we begin, do you guys have any questions or comments you want to go over?
I think, I don't know, or were you going to spend any more time with the auxiliary particle filters? Because I think some of us were a little confused. Maybe we can talk about it during the homeworks. I was able to actually implement it, but I just don't understand what it was doing.
Okay, sure. So I hadn't planned to spend any more time talking about auxiliary particle filters except when we use it in examples. But that was all I was planning on. So if there are ideas that were a little bit vague, or if you want to go back to some of the slides we went over on Monday, I'm happy to jump back to those and spend some time going over those before we move into the homework presentations for today. Should we do that?
Maybe just when you present the examples, if you go into a little bit more detail in the context of the example, but I don't know what everybody else would prefer. Because I agree there were a few things that were a little fuzzy, but maybe in the context of an example it would be more clear. And
one of the things I haven't been doing that may also be helpful is looking at code. And as you know, I'm sort of not risk adverse. Let me see if I can bring up the code. And maybe I can use that to answer some questions. We'll see if this works here. Oh, great. Looks like it is. Nice. So we can get to the code. All right, so this was the code that I used to generate the examples. And I think this is the actual code that's going through and doing the auxiliary particle filter. It's funny, we spend an entire lecture on this. These are really difficult concepts, but once you get it coded in, it's like 20 lines. It's cool that it's that concise. But Sam, were there particular ideas, or would it be helpful for me to step through some of this code?
Well, it seemed like basically you're resampling every time, right? Isn't that one way to think about the auxiliary particle filter? You're resampling every single time?
The only thing I would change is to say pre-sampling rather than resampling. But yes, you're pre-sampling every single time. And there are some people that say, with the simple particle filter that we covered the first time, the first version, the simplest version, some people say, just go ahead and resample it every time step. There's no reason not to, other than the computational expense. And so some people are of the mindset that, not unlike the auxiliary particle filter, you should resample every time. And just as I mentioned with this, when we're moving our moving our particles forward in time, that we could use we could blend this together with the sort of approximate optimal particle filter based on the linear state model to move the particles forward in time. The other thing that we could do is, after we calculate the weights, which is down here. I don't have a resampling scheme after the weights are calculated, but you could go through and resample based on the weights if you wanted to. And some people say with the auxiliary particle filter, you should do the resampling step also, and you can do it at every time step and not just when you hit a threshold of dropping below the number of effective particles. So all the versions and generalizations of particle filters that we've talked about so far could be actually combined into one. With the auxiliary particle filter where you're doing all of the tricks for improving it that we've talked about. That may add more confusion than help.
So you can pre-sample and resample is what you're saying?
You can pre-sample and you can resample both in one algorithm, and that's just fine. It doesn't break anything. It's all consistent. It's usually unnecessary because the pre-sampling eliminates the degeneracy problem. But this is the pre-sampling, and it's using what we talked about. Notice this is, rather than the particles, this is where we're taking the particle at time n-1 and essentially using our system model or our process model to move it one step into the future. So this is really a predicted value of what that particle will be. And then you run it through the measurement model, and that's our value of y that we're evaluating this at. So it's exactly what we talked about in the lecture. In this section here, I guess I should be trying to use this as the pointer. This section here is the pre-sampling step where you're going through and picking your parents. I'm not sure. Did you use this code as a starting point?
I did, yeah.
Yeah.
And I've seen that code before. It's
So,
very familiar.
Yeah.
But, I guess it's a little tricky. I mean, I guess I see what it's doing, but I don't know. I guess maybe I'll just take another look at it. I actually have a plot of some of the trajectories for both the particle filter and the auxiliary particle filter that maybe can bring up more questions, and maybe we can...
Good. One of the points that may confuse you, if you're looking at the particle trajectories, they look strange. And part of the reason they look strange is that at each time step, a particle may get a new parent. And that makes it more difficult to plot what the particle trajectories are. So the plotting may look like there's a lot of crossing over, and that's due to this pre-sampling. It's a little bit different than resampling, where we tend not to run into that problem.
Well, so like with the traditional particle filter, you can have like a weight for one particle that's, I would say, sort of gradually grows until it's, the highest, and then you resample. At least that's how I implemented it. But it seems like every time step, you'll get a few new particles that have strong weights that aren't necessarily the same, or they're different, I guess.
Well, we're resampling with replacement, so some of the prior trajectories at a point in time we abandon. They're not picked if they've got a low probability, and some are picked. And it depends on what the probability is that we calculate. We're picking the probability with which we pick those. So some are abandoned and some continue on at every single time step. There's parents that are getting left behind, and some parents are allowed to propagate sort of more than one particle forward. And that's okay. I mean, that's by design. It's what it should be doing. So, are there other questions on auxiliary particle filters? All right. Well, and I'll try to spend a little bit more time maybe going through the code. Now that I see this works and I can actually easily get to the website and pull up code examples, that may help as well. But yeah, thanks for asking the question and giving the advice.